This is the cylinder lab report for Caden, Jeff, Liam, and Martin. In this lab, we examined cylinders, which are well known for having high drag. This is due to the boundary layer separating as the air flows around the cylinder against the pressure gradient. This causes low pressure in the wake along with vortex shedding. The goal of this lab was to determine where the flow separates from the cylinder and whether a trip strip can help delay this. In this experiment, a cylinder with pressure ports located around its circumference was placed in the test section of the wind tunnel. Smoke visualization was used in order to observe vortex shedding behind the cylinder and determine how this is affected by the Reynolds number. This is examined more in the methodology. This is a summary of all the variables used in this lab. A cylinder was mounted in the wind tunnel with 24 pressure ports around their circumference. Smoke was used to visualize flow, and data was taken at an airspeed of 0, 5, 10, and 25 meters per second. After 2 datasets of these speeds, we did 2 more datasets after attaching a trip strip to the cylinder to add more energy and turbulence to the flow. These are the equations we used in this lab to calculate the Strahl number, the coefficient of pressure, total pressure, and the coefficient of drag.
Let's take a look at the videos for 5 meters per second with the trip strip and without the trip strip. The expected result of this part of the experiment was that the flow would separate later for the trip strip than without the trip strip. The reason for this is that the trip strip trips the laminar boundary layer and makes it turbulent. The turbulent flow has an easier time overcoming the adverse pressure gradient in the wake of the cylinder. Let's take a look at the data for this. From the theoretical flow solution, we expected for flow separation to happen at 90 and 270 degrees, which correspond to the top and bottom of the cylinder. Looking at 90 degrees, there's not too much going on, but if you look at the 270 degree region, you can see that the purple and yellow lines, which correspond to the trip data, delve much deeper into the negative values of CP. And these negative values of CP are lower than the negative values of CP for no trip, which means that the numerator for the equation of CP must be more negative for the trip data than the no trip data, which means that the static pressure at these theta must be lower for the trip data than for the no trip data. Then moving this to the equation where stagnation pressure is equal to P static plus P dynamic, this must mean that the dynamic pressure is hence also larger for the trip data for these thetas than the no trip data. This in the end means that the velocity for the trip data at these thetas is higher than the velocities for the no trip data at these same theta. This in the end means that the trip strip is doing its job of keeping the flow attached for a longer time. If you look at this green plot, this is the theoretical flow plot. At 90 degrees and 270 degrees, you have points of inflection where the flow changes between acceleration and deceleration, and at 180 degrees, you have CP equal to 1 where the flow is completely stagnated. Now let's take a look at the 10 meters per second flow visualization with the trip strip and without a trip strip. This higher velocity corresponds to a higher Reynolds number, so both of these visualizations should have a later point of flow separation than the 5 meters per second test. And the trip strip should have a later point of separation than the no trip strip test. The apparent difference in velocities of the flow has to do with the different frame rates that these videos were shot at. Taking a look at the plot for no trip versus trip at 10 meters per second, you can see that there's not much going on in the 90-degree region, but there is a change that has occurred in the 270-degree region. The purple and yellow lines are delving even farther into the negative values of CP, which that means that the increased velocity with the trip strip is doing an even better job of keeping the flow attached to the cylinder. Let's take a look at the 25 meters per second test. On the left side we have no trip strip, and on the right side we have trip strip. This is the highest velocity we tested at, and this should correspond to the highest Reynolds number that we tested at. So both of these cylinders should have a later point of separation than all the other tests we ran, and the 25 meters per second with the trip strip should have the latest point of separation out of all of our tests. Take a look at the data for 25 meters per second for trip versus no trip. At 90 degrees, again, not much difference, but at the underside of the cylinder at around 270 to 320 degrees, we have the lowest coefficients of pressure and sustained for a longer time than 10 meters per second and 5 meters per second. This corresponds with the idea that a higher Reynolds number with a trip strip will produce more turbulent flow, and therefore the flow will stay attached for a longer time. This is a plot of the standard deviations of the pressure data with no tape. The sharp drop at 210 degrees corresponds to port 2 on the cylinder, which was malfunctioning during our testing. The standard deviations increase with an increase in velocity, and this is because the turbulence increases with increase in velocity, and this adds more variation to the flow. Here are the standard deviation plots for the tape experiments. The biggest difference to notice here is that the standard deviations for 5 and 10 meters per second were lower here than for the no tape experiment. Let's take a look here at the effect of high RE on the point of flow separation. As you can see here, there's not that much that has changed. Versus in the previous plots that we were looking at, the trip strip made a huge difference in the values of CP and the prolongment of these larger negative values of CP. So from this we can conclude that the trip strip is more effective at making the laminar boundary layer flow turbulent at an earlier point, and therefore making the flow more capable of overcoming the adverse pressure gradient on the back side of the cylinder, and therefore keeping the flow attached longer.
The Strohel number is a dimensionless number that describes a vortex judging around a shape. The left plot is a calculated Strohel number for this experiment, and the right is the theoretical values. It makes sense that the trip strip Strohel number is lower than the non-trip strip Strohel number, since the flow is attached to the cylinder longer, making for an even lower pressure behind the cylinder and less vortices than no trip strip. Based on plots found online, such as the one on the right, we expected that the Strohel number be closer to 0.2 as opposed to 0.5. This is most likely largely due to the error in our measurement of the frequency, since we're using phone cameras. The higher frequencies seem to be closer to the ideal plot.
Here we have the expected plot for the drag coefficient versus the Reynolds number of a cylinder. Notice how the graph follows a curve in which the drag coefficient of the cylinder decreases as the Reynolds number increases. This plot displays an easy-to-read trend. When we get to the plots generated from measured data, it should be noted that the drag coefficient was calculated at discrete velocity measurements. Therefore, we are left with points on a plot as opposed to a curve. However, a trend can begin to be established. When taking data without a trip strip on the cylinder, the drag coefficient is higher than with a trip strip. The trend then shows an increase in drag coefficient with an increase in the Reynolds number. This is the opposite of the previously displayed graph. It is difficult to compare the results of the drag coefficient versus the Reynolds number plots due to our measurement being taken at discrete velocity values. It is likely that the opposite trend than expected being displayed is due to a misinterpretation of the data.
In this experiment, the flow is treated as two-dimensional. The wind tunnel is well designed to make the flow go in a single direction. The flow does this until it gets to the only major obstacle, the cylinder. Because the cylinder went all the way to the sides of the tunnel, the flow could only go over it or under. The flow continued in only two dimensions. The trip strip and other surface roughness created a turbulent boundary layer. While some of the turbulent air might have moved in 3 dimensions, the flow as a whole only moved in 2. In this experiment, a trip strip was used to make the boundary layer turbulent, but a similar effect could be caused by any form of bump, roughness, or imperfection. In laminar flow, everything is orderly and fluid particles do not interchange layers. In turbulent flow, the fluid particles move more chaotically, including perpendicular to the flow direction. This results in turbulent boundary layers being larger than laminar layers and creating more friction drag. While turbulent boundary layers are larger, the velocity gradient in the boundary layer increases faster. At the front of the cylinder, the flow is accelerating and has an advantageous pressure gradient as the pressure falls along a streamline, helping the flow to accelerate. The effect of this is to counter some of the friction effects and limit the growth of the boundary layer. After the widest point on the cylinder, this favorable pressure gradient no longer exists and the boundary layer grows quickly. The flow separates when the boundary layer grows big enough that the deceleration reverses the direction of flow near the surface. Because of the shape of the laminar velocity gradient, laminar flow separates easily, while a turbulent layer can grow much larger before the reversal and separation. By creating a turbulent boundary layer, friction drag is increased, but the flow can stay attached longer, decreasing the pressure drag. For a bluff body, this exchange is worth it. Separation cannot be done away with completely in real fluids due to the viscosity of fluids, but there are several ways to mitigate the problems of this vortex shedding. Vortex shedding caused oscillating lift and down forces. The center of the low pressure shifted up and down depending on whether the top or the bottom was currently shedding a vortex. With the trip strip affecting the point of flow separation on the top and not the bottom, there was a trend for the oscillations downward to be greater than the oscillations upward. This caused a bias towards downforce with the trip strip. All cylindrical structures need to deal with the vibrations from alternating forces caused by vortex shedding. A common strategy is to disrupt the flow. This can be done with rough surface, splitter plates, or helical strakes. The size and pitch of a helical strake is correct and greatly reduces vortex shedding by increasing the turbulence in the boundary layer. They're used for chimney stacks as well as in some car antennae. Another method is to allow the vortex shedding but to damp the resulting vibration with a tuned mass damper. This is the method used in many tall buildings. Power lines use one called a Stockton damper to transfer the vibration of the main cable into a short cable of specific stiffness, specific masses at the end. These are tuned to attenuate the high frequency vibrations from the vortex shedding. Reducing these vibrations reduces cable fatigue and extends the life of the cable. The effect of a turbulent boundary layer applies in 3 dimensions as well as 2. Because of this, a sphere experiences high pressure and oscillating vortex shedding just like a cylinder. The difference is that vortices can be shed in any direction instead of in just 2.
Based on the data collected and analyzed in this lab, it is evident that the boundary layer did in fact separate partway over the surface of the cylinder. This is shown by plotting the coefficient of pressure versus angle of the pressure port it was measured from. Furthermore, as seen by the smoke visualization, the rate of vortex shedding increased significantly with an increase in Reynolds number. resulting in a lower Strohal number as Reynolds increased. There are several areas that are possible sources of error, including pressure ports that were not working and human error while attempting to measure the rate of vortex shedding. It should be noted that the standard deviation of calculations significantly increases with an increase in velocity.